Hello, hi, my name is Isaac, and you're most welcome to this lecture series for Engineering Mathematics TCEM 1101 for first years 2021. I'll be taking you through a part of engineering mathematics where we are going to be looking at some concepts in the linear algebra. This is a very important area in applied mathematics, and it is used in solving so many problems in engineering. Later on we shall see, as you go on studying so many other areas of applied mathematics, e.g. differential equations and partial differential equations, and you study some of these numerical techniques, you will see that everything is we apply all of these areas, like from maybe you can start with a problem which is a partial differential equation, then you get into numerical techniques, and then you find yourself ending up in linear algebra before you can get some of these solutions to many of these problems in applied mathematics. So it's a very important area. However, this is by no means exhaustive, because here we're just looking at a few concepts. As you can see, the course was just designed for 8 hours. Yeah, and yet there are people who study this linear algebra for, I don't know, for a whole semester and another semester and another semester. And there are those who master in some areas here, and then there are those even who do PhDs in these techniques. So this is by no means exhaustive. However, it is good for us to have an idea what is happening here. So the textbook which we shall be using, of course we shall be using quite a number of resources. However, the textbook for which I'll be sending you a link to is one which I like because of its simplicity, and it is called, let me write it here, Matrix Analysis and Applied Linear Algebra. So this is the book, Matrix Analysis and Applied Linear Algebra, and the author is a gentleman. Let me just write it down here. This is Carl D. Meyer. Yep. And then I think these are the editors. SIAM, Society of Industrial and Applied Mathematics. Why I like this book is that it has a test of both the theoretical, which is mainly under this matrix analysis, and then it has an emphasis on the application, since I think the people who reviewed this come from the Society of Industrial and Applied Mathematics. Yeah, so I'm not sure if I told you my name. I should have told you that first. So my name is Isaac. Boy. So you will please forgive me if the quality of this video is not so good. I am having so much background noise, so occasionally you may hear a car, a vehicle, or a boda, or even the birds in the background. I am so sorry, I have no control over that. However, next time I will find a more secluded place, perhaps studio-like environment, where I can cut out all the background noises. Nevertheless, I hope I am really audible and the video quality will be nice, so we can start off with our learning here. So this is the course. These are the topics. Should I say topics? These are the areas which we are going to look at. We shall look at systems of linear equations, okay, and then we shall look at vector spaces and subspaces, basis and dimension. We shall look at this concept of linear dependence. Then we shall go through the basics of matrix algebra, yeah, the matrix, transpose, addition, and so on. Then we shall look at linear systems. These are very important here. These are very important in the world of applied mathematics or engineering. And then we have elementary operations, echelon matrices, and we shall look at other types of matrices, and then we shall look at determinants, permutations, and everything else that is in here. We shall try to go in detail, and then though the course does not offer for the course is simply like we just look through this and yeah, we just look through what is outlined here and have an idea what is going on, computing this and that. But I would like to add a test of some computing, some computations. It is very unlikely that whatever you're going to do out there in the world, you're going to do it by using manual computations. Like, the computations in the real world are quite heavy, and they are always used with the help, solved with the help of computers. So it would be good for us to learn a package or two and just carry out some of these computations to see how these things are done practically. So with that in mind, perhaps the easiest I think we could think of is MATLAB, but I will let you know this later. So we may have a few assignments which you shall do in MATLAB. I can also give you a series and show you some of these things, how we can do them. So this is not on the course outline, that is what I was trying to say. However, it is very important for us to know, since we are applied mathematicians, how to use some of these computation tools. Yep. So yeah, we could start going, and then I will follow the book. I will send you the link to the book, and yes, so we will start right now. So what else do I have to tell you? Oh yeah, I'll be uploading this lecture series on YouTube for now, so you can be able to watch them during your free time. And then when we log in for the online sessions, we will be having a discussion. Spelling? Yeah, we'll be having a discussion on what was in the lecture series that was posted on my YouTube. For now, I hope that will work, and in case you have any problems or any complaints, be free to let me know how I can make this better, because this is the first time I'm teaching using this mode, so I am sure it may not be the best experience for some of you, or the quality may not be the best. However, I am open to criticism, and yeah, I hope I can always improve on the delivery of this series here. Okay, so where else can I start? Let me see. Yeah, the purpose. I have taken you through the purpose. I've given you a brief background and so on. Yep, told you. What else? I'm trying to think about what else you need to know before we start off. And yeah, something important here. Yeah, what does the term applied mean? So most people agree that linear algebra is at the heart of applied science. Maybe you realize that later on. However, there are some divergent views that concern what applied linear algebra really means. Well, I don't want to go into this discussion here, but I would like to think that applied linear algebra is mostly has has to deal with the computation aspects. Yeah, like we study, of course we don't want to limit our study here to just an academic, you know, an academic procedure, like we study what is this, what is this, what is this, and then we stop there. No, we'd like to go ahead and apply it, so that is why I would like to call it applied, and where we shall have some computing projects here for us to see how we can apply this in real life. Okay, so I would like to start with dealing with maybe I go to the next page. So what am I going to start with? I would like to start with linear equations. Linear equations. Maybe what you have to know is that if there is linear equation, then there must be non-linear equations. But this we shall see later on. Let us assume for now that we know what a linear equation is. Okay, I don't want to go into the definition that this is linear, this is non-linear, and so on. Let us assume that everything I am going to write is a linear equation. If it is non-linear, or if we get to that part, I will let you know the difference and so on. So we see that a fundamental problem that surfaces in all mathematical sciences is that where we have to analyze and solve M algebraic equations in M unknowns. Let us assume that we have M equations, okay, and then we have N unknowns. We will see later on, of course, when we have studied so many other areas. I presume this is our first lecture in engineering mathematics, so I don't want to preempt what others will tell you. However, if you do some differential equations or partial differential equations or numeric analysis, we shall see how mainly we can come up to such systems of equations where we have a number of equations with a number of unknowns. So right now we are just going to look at some of the simple ways of how we can analyze this. Okay, for instance, let me see here a simple example. Okay, let me just write down a simple example here. Supposing we have this system, we have 3x, let us assume x, y and z are unknowns, and then we have this equation. You have equation 1, and then you have 2x, 3y and z, and this is 34, and you have x plus 2y plus 3z, and you have 26. So this of course can arise from, like, let us assume that we have a word problem which led to us having such equations which are written in this way. Maybe this could be the number of items, and let us assume maybe this could be the price. So maybe something like that, that you have the number of items times the price, and then you have the number of items times the price, and then maybe this on the right hand side is maybe, let's say, the cost for each combination, cost of each combination. Maybe you went to the supermarket, you bought some yogurts, you bought some chocolates, and then maybe you bought a loaf of bread. I'm just assuming something like that. So yeah, this is just a simple example, but what you should know is that such in the field of applied mathematics, we shall call them systems of linear equations. Now, linear, maybe to give you a hint, we have to deal with the degree of the unknown, or let me say the highest power of the unknowns. So for now we see that all of these unknowns, the power is 1, so that is why we call them linear. Okay, if it had anything which was not 1, maybe x to the power 2, then we would not be calling that linear anymore. Okay, linear in that the unknowns are all raised to the power 1. Okay, so this is very simple, but I was trying to say that in the field of applied mathematics or engineering, the systems that arise are very large. The systems that arise are very large. So what we are going to do here is just to look at, just analyze how we can analyze such a system. Okay, we start with a very simple system for which we can analyze. Then in the world of applications, systems which are really large, really large, you will have to use a computational tool, okay, which you can use with the help of a computer. So however, the importance of using these computational tools, having known how to analyze simple systems, is such that you can be able to analyze the nature of the solutions you have, or at least have an idea if anything wrong is happening. Alright, because yeah, these are also prone to error. So you can always know that maybe something is not right here, something is good here, or I need to analyze this in such a way, and so on and so on. So we are going to look at how we can maybe solve some of these, and the first name, or the first method that we are going to look at is called the Gaussian elimination. Okay, so you can go and search or Google the gentleman, this famous, I don't know whether to call him scientist, mathematician, he was just all over the place, Gauss, and read a few things about him, what he did and what his contributions are to engineering or to mathematics or to science and so on. So now, what does Gaussian elimination tell us? I would like to write down our simple system which we wrote previously. Now we would like to write it in a general form. For now. Let me write this way. I'm going to explain to you in a short while what these indices mean. I told you to please excuse me if you hear some background noises of a motor vehicle, boda, or the birds. Those I have no control over for now. Okay, so we have this is 1, x1, and I write that, and that, and that, and I write b2, then we have that, this is 2, and mn xn, yep. Okay, so in here what we have written is a system which consists of m equations. I will explain to you. M equations and n unknowns. In other words, we have equation 1, equation 2, up to equation m, and then the unknowns, you have the first unknown, you have the unknown, the second, and so on up to the nth unknown. Okay, so we are going to say that the xi's are our coefficients or unknowns. The coefficient. No, the ages. Sorry, not the i's. Sorry. We have the a. Okay, the number n is not. This is. I should maybe say that this n is the number of unknowns, and then m is the number of equations, and then you have these coefficients, the a's here. Okay, let us write them using this notation: a, I, j. We are going to say that these are the coefficients of the unknowns. Alright, then we have a right hand vector here, which is b. We shall say this is the right hand vector. Okay, so now here, general notation, we shall count along. If we say we shall count along each row using I, and then we shall count along if it's not a row, what is it? Column. We shall count along the columns using J. Alright, so that means that this is I is 1. Okay, let's say this is I is 1, I is 2, and so on up to I is m. Alright, and then along the columns what can I use? Okay, along the columns we shall say, oh sorry, not I, j is 1, maybe j is 2, and so on up to j is equal to n. In other words, we have column 1, column 2, column 2, 3, and so on until column n, and then we have the rows 1, 2 up to m. Okay, so you can clearly see, that means I made a mistake here, because if this is column, this is row 1, row 2, then this should not be n, but rather this should be m. Okay, because it is first row, second row up to the nth row corresponding to this, and then these are the columns 1, 2 up to n. Okay, so what have I left out? I have said xi is the unknown. Okay, so let us write it here, and in summary we are going to say that we have xij, which we are going to call the unknown. Then we are going to say, why am I being sloppy? It's not xi, which is the unknown, rather xj is the unknown. Alright, and then aij is the coefficient of the unknowns. By the way, if I make, not that if, I am sure I'll make a mistake here or there, you can always put it in the comment section. okay, so that you can help your friends and help me so that I can correct it later. So we have the unknowns, we have the coefficients, and then we have bi, which is the right and vector. So now these the indices which I was writing, 1 1 would simply imply, for instance, a11, this one here. Why did we write a11? A11 of course implies that we have I is 1 and j is 1. So it is the coefficient of the element which occupies, okay, row number 1 and column number 1. Okay, so if we wrote 2 1, that would be the coefficient of the element or entry which occupies the position which is in row number 2 and column number 1. Okay, so that's just the notation which we use. And then in general, if we write it a mn, this would be the coefficient of the entry which is in the mth row and nth column. Okay, yep. So I hope I haven't forgotten anything else about what I wanted to tell you. We have the system there, how to name it and how we label, and yes, some of the simple terminology. Now, so what's with this system? I would like to analyze that system. Oh, by the way, so the simple example which we had here, this was just a system here where we have how many equations? 1, 2, 3. So we have m is 2. Oh, sorry. I counted 3, I wrote 2. That's crazy. M is 3, 1, 2, 3, and then the rows, and then the unknowns, we have x, y, and z. So we have 3 unknowns. N is 3. Yeah, so this is a system here which consists of, we shall read it 3. Okay, we read it 3 by 3 and then we write it that way, 3 times 3. This is read as 3 by 3. Alright, so that is how, this is the size, so we call this the size of the system here, the size of this system here. Okay, 3 by 3. Okay, yeah, maybe someone would ask that, what about the right hand vector? Well, we don't, if we are talking about the size of the system, we exclude this right hand vector. Don't mind about this, we shall just say count the number of equations here and then the number of unknowns. Okay. Okay, so let's go. So we want to make the analysis here of our system here of size m by n. Alright, so 3 possibilities could arise here. One, that we could be faced with a situation where we have what we call a unique solution. Okay, i.e. there is only one set of values that satisfies the xi's. Okay, in other words, that each of the xi's has just one value for which we can get from this when we compute the solution. Second scenario is that we could have no solution. Interesting. Yeah, that is quite interesting. Yeah, and this is quite these are very interesting problems to work with, especially in the world of let me see. Well, okay, I'll come back to it later. I don't want to fly off the tangent at this point. Let me stick to the script here. And then we could also have a situation where we have infinitely many solutions. Yep. So we have a case where we have a unique solution. Some people I think say one solution, but I don't want to use that. Sounds not nice. We have a unique solution, have no solution. In other words, the solution set is empty, or you could have infinitely many solutions for each of the xi's. So now, before we get to that, before we get to how we can see whether the system has a unique solution, it has no solution, or it has infinitely many solutions, there is something important which you have to look at here, and these are called okay, let us look at the procedure of the Gaussian elimination. Remember the name Gauss? Yes. We say that we are going to use the method here, which is called Gaussian elimination tool, and the Gaussian elimination for us to know or analyze this system and find out whether it has either one of those three cases there. So that drives us to what we call some operations here, some elementary row operations. Okay, now let's start with this. How do we start? Let's say, we shall use the letter E. Let us say EK to describe the kth equation. The kth equation. What do you mean? Kth equation. Let us assume this is I is 1, I is 2, and then maybe in the middle here you had I is k. So let us just pluck out that equation here. Okay? Maybe for I is k. For I is k, you just substitute ak1. Okay. So this would be ak1, x1, and then what would this be? A k2, x2, and so on. And this would be a kn, xn, and then here would have bk. Okay, so let us assume that we have that ak1 x1 plus ak2 x2 plus akn xn, and then we have the right hand side bk. Okay, now let us write our system S. Let us say that S the system. Of course, the whole system is going to be comprised of all the equations. So maybe we have equation 1, then we have equation 2, and then let's say we have up to the nth equation. Let us say this system here, which has m equations and n unknowns. Okay, let us represent it that way. So we are going to look at the three elementary operations. Three elementary operations. Okay, yeah, I think I can call them row because we are going to apply them to the rows here. 1. If we interchange the ith and jth equations, interchange ith and jth equations, what are we going to do? Interchange. In other words, it's just as simple. If we have S written as it is here, and then we carry out this interchange ith and jth, let us assume that we come up with a new system which we can call S prime. It's simply going to be the system where you have E1, E2, okay, it's not a great idea. Maybe since I don't have I and J in S, maybe let us write it this way. Maybe it saves a lot of time. Okay. Let's do this. Let's say we have S, we have E1, E2, and so on. Then we have EI, and so on. We have EJ up to maybe EN. So if we interchange the ith row and jth column, we can come up with S prime, which is the same. Okay. Only that maybe where you had I, now you replace it with J, and then where you had J, you now replace it with I. It's just that, just switch where the ith row you put it in the position of J, and then the jth row you put it in the position of where I is. That's it. Okay, that's as simple as that. So let us look at another case, okay, where we are going to replace, what do? We replace the ith equation. Oh, by the way, please note that the usage of I and J in this case is not necessarily that this is the number of row and then this is the count for the number of columns. No, we are just using it as an index, just as a count, that this is 1, 2, 3, 4, I, then up to J, up to N. Okay, so please don't get confused. Maybe I's could have been maybe 4 and then J maybe 7 and stuff like that. So that means that what was in the 7th position, you put it in the 4th position, and then what was in the 4th position, the equation that was in the 4th position, maybe you put it in the 7th position. Okay, so the other, we are saying that we replace the equation which is in the ith position by a non-zero multiple of itself, In other words, let's assume we have S as defined here. Alright, so what would S prime be? We are replacing it by a non-zero multiple of itself. We would simply write E1, E2. So what else would we have? Maybe you have alpha times EI, then you have maybe EJ up to EM. In other words, you have replaced the equation which was in the ith position, in other words EI, by a non-zero multiple of itself. Of course, that implies that alpha is not equal to 0, non-zero multiple of itself. Okay, and then 3, we are going to replace the equation in the jth position by a combination. Okay, let me write it here. We replace the jth equation by a combination of itself and not and, rather plus, okay, a multiple of the ith equation. Please note the order here. We are saying that we are replacing the equation in the jth equation by a combination of itself, please note the English, itself plus a multiple. So the multiple is of the other equations which we are bringing. Okay? In other words, we would have our s prime written as, let's say we have e1, we have e2, e3, okay, then we have ei, then we say that where we had ej, we say that we replace it with a combination of itself, that is ej, plus a non-zero multiple of the ith equation. Okay, so in other words, you get ej, you replace it with itself plus a multiple of the ith. Please note that this is very different from if you had written it this way. Okay, that is quite different. Okay, so now all these three operations, 1, 2 and 3, will result in a system which is equivalent. Will result in a system which is equivalent. We have said that 1, 2 and 3 result in an equivalent system. In other words, the system S prime we have here, okay, or the system S prime we have here in 2, okay, or the system S prime here we have in 1 is equivalent to our original system S. Okay, now you shall see that it does not change the nature of the solution. Okay, so now we can pause here a little bit, and then in the next segment we are going to actually look at how we can carry out these three operations and carry out Gaussian elimination to solve the equation. Okay, so you can take a water break, and see you in 5 minutes. All right.